Okay, you notice how I start every lecture with okay? Particle wave duality, prelude to quantum mechanics. The goals are to understand that in the modern view of the atom, electrons can be either particle or waves. Calculate the wavelength of a particle using de Broglie's equation. Okay, so let's take a look here. The particle wave duality. Turns out that we just talked about with the photoelectric effect, you can describe light as massless particles called photons, packets of energy, as it were. So, in other words, light can be described as either a wave or it can be described as a somewhat particle type of behavior. Well, we can flip the script and say, well, if we can do that for light, which has no mass, can we do that for something that does have mass, which is definitely a particle? Could we treat them as waves? And so indeed, this has been done. So here, particles, electrons do have a mass, so it's not hard to conceive as electrons as particles. But the flip on the script is that we are going to treat electrons as if they are waves. And so we have this something called the de Broglie wave equation. Now, there is precedence for this, and it has to do with scattering of electrons. If you look at the scattering of light through a slit, if you will, you get something that looks like a bullseye type pattern. And pretty easy to understand if you know anything about light and diffraction and all of that stuff. But since this isn't a physics class, we're not going to go there. However, another interesting thing is if you take an electron beam and you shoot it at, say, aluminum foil. So if you shoot light at aluminum foil, you get a nice bullseye pattern. If you shoot electrons at aluminum foil, you'll also get that bullseye type pattern. So it seems that the electrons, the particles, are behaving like a wave. So de Broglie came up with this idea for the wave equation, where the wavelength of a particle is equal to Planck's constant divided by mass and the velocity of the particle. Now, I'll be honest with you, this wave equation is really only good for very, very small particles. The other thing about this wave equation, for this equation to work, the mass must be in kilograms and the velocity must be in meters per second. And we'll see why in just a minute if I can remember how to derive this equation. So let's see if I can remember how to derive this equation. And actually what I'm going to do is a little something different. So we've got wavelength is equal to h m over v. And here, the wavelength is going to be meters. Planck's constant is joules seconds. Mass is kilograms. I'm going to write that in. And velocity is meters per second. Now, it turns out that a joule is a specific type of unit. It's a kilogram meter squared per second squared. So here's my joule. I'm going to put that in parentheses. Here's the kilogram meter squared per second squared. And here I still have kilograms for mass and meters per second for velocity. Okay. So everything corresponds with other things. And you just have to believe me for the moment that a joule is a kilogram meters squared per second squared. The way I was taught about this in physics is that this is a kilogram meter per second squared meter. So when you talk about energy, the amount of energy depends on basically three different things. So here we're going to talk about taking a object and making it move. So if you take an object and push it along and you don't change its velocity, that is, you don't accelerate it, and it's on just a airless track, you don't actually have to keep pushing it. So if you put it on a frictionless track and you push it, it just keeps going at the same velocity forever if you don't put energy into it or don't take any away. So, that is kind of like the bullet train in Japan or trains like that, where they kind of levitate on the track through this magnetic repulsion. You reduce friction and they go forever, and you don't have to put much energy into them. So here, what does require energy? Well, the larger the object, the more energy it takes. So that's taken care of here in this kilogram. Meters per second squared is called acceleration. Now, I said that you don't have to put energy into an object if you push it on the track and just keep it at the same velocity. You can let go and it keeps going at the same velocity. But what if you wanted to increase its speed? Then you'd have to put energy in. To increase the speed is called acceleration, and that's meters per second squared. So let's say you have an object of a certain mass that you're accelerating. Well, what else requires energy? The distance over which you accelerate it. So if you accelerate it over 1 meter, it's going to take half the energy as accelerating it over 2 meters. So here's the distance. So this is like mass times acceleration times distance. All of those affect the amount of energy you put into something. So back to this. Let's see how this all shakes out. This second cancels with one of these seconds, so I'm going to just get rid of the 2 there. Here, this second is in the denominator, so that cancels with this second in the denominator. Here, this meter squared in the numerator, one of them cancels with this meter. This kilogram cancels with this kilogram, and you get a meter is equal to a meter. So the object lesson here is that a joule is a kilogram meters squared per second squared. So for everything to cancel, when you use this equation, you have to get the mass in kilograms and get the velocity in meters per second. If you don't do that, the equation is not going to work. If you do that, your answer is going to be in meters. Okay, so now that we know that, let's take a look at this. Using the Broglie wave equation, calculate the wavelength associated with an electron of mass 9.109 times 10 to the minus 28 grams that travels at 40% the speed of light. Okay, so we know that wavelength is equal to, let's see, is equal to H over mv. So here's the wavelength. So when we talk about these values, here's the mass. So the mass is equal to 9.109 times 10 to the minus 28 grams. I want to convert that to kilograms. So I'm going to multiply by 1 kilogram over 1,000 grams. And we're going to get 9.109 times 10 to the minus, let's see, that's -3 or +3 now, minus 31 kilograms. Okay. For the velocity is 40% the speed of light. So what does that mean? That means 4t over 100. So here we avoid just moving the decimal over 2 places because that is just fraught with error and potential disaster. Percentage always means take that number and put it over 100. That's the definition. So that's the way we use this in our class. Now times 2.998 times 10 to the 8th meters per second. And you can see we're going to get a value that's 40% of that. Let's see what that is. 2.998 second EE 8 times 40 divided by 100. And I get 1.199 times 10 to the 8th meters per second. So there's the mass, there's the velocity. And remember, Planck's constant is 6.626 times 10 to the minus 34 joule seconds. So when we plug all this information into this equation, we get this. Lambda is equal to 6.626 times 10 to the minus 34 joules seconds, 9.19 or 109, 9.109 times 10 to the minus 31 kilograms. And the velocity is 1.199 times 10 to the 8th meters per second. Now, remember, since that's in kilograms, since that's in meters per second, my answer here is going to be meters. That's a lock, okay? So let's see what we get. 6.626 second EE negative 34 divided by 9.109 second EE negative 31, and also divided by 1.199 second EE 8, and we get 6.067 times 10 to the minus 12 meters. So is this visible light? And the answer is no, because this is the same as 6.067 times 10 to the minus 3 times 10 to the minus 9 meters. Do you see how I took the 12 and I separated that into minus 3 and minus 9? Because minus 3 and minus 9 equals negative 12, which is the same as 6.067 times 10 to the minus 3 nanometers, which is 0.00667 nanometers. And visible light is 400 to 650 nanometers. So this is not visible light. Okay, so that is the wavelength associated with an electron moving at 40% the speed of light. It's a pretty short wavelength. Remember, short wavelength means high energy. Let's do another calculation here. And for this next calculation, instead of calculating the wavelength associated with that, well, here's another one. Let's do this one. An electron moves with a velocity of 2.5 times 10 to the 8th centimeters per second. What is its wavelength? Okay, so here we're going to use the de Broglie wave equation again. Wavelength is equal to h over mv. So here we need to find out what m is. So m was given to us before. It's equal to 9.109 times 10 to the minus 31 kilograms. Notice I'm using the number we calculated before. And the mass is this. The velocity is that. Now, what's the problem with our velocity? The answer is it's not in meters per second. So I'm going to multiply by 100 centimeters on the bottom and 1 meter on the top to convert it to meters per second. And we'll get 2.5 times 10 to the 6 meters per second. Okay, and then Planck's constant, of course, is 6.626 times 10 to the minus 34 joule seconds. So now we can plug everything in and see how it all shakes out. So I'm going to start kind of fresh over here. Lambda is equal to h over mv, which is 6.626 times 10 to the minus 34 joule seconds, and then divided by 9.109 times 10 to the minus 31 kilograms, and then also divided by the speed, which is 2.5 times 10 to the 6 meters per second. So again, why did I change the centimeters to second to meters per second? So that everything will cancel out and I'll end up with meters here. So we have 6.626 second EE negative 34. Whoops. Divided by 9.109 second EE negative 31. And also divided by 2.5 second EE6. And I get 2.9 times 10 to the minus 10 meters. Okay, I'm going to rewrite that. 2.9 times 10 to the minus 10 meters. That way you can see it more easily. And so there's the answer to that. All right, one more here. Calculate the wavelength in nanometers associated with a 46 gram golf ball traveling at 30 meters per second. At what speed must the ball travel to have a wavelength of 5.6 times 10 to the minus 3 nanometers? So we have two questions here. Let's start with the first one. Wavelength is equal to h over mv. Now, we've got to take that 46 grams and turn that into kilograms. So 46 grams times 1 kilogram over 1,000 grams is going to be 0.046 kilograms. Okay. All right. The velocity we have as 30 meters per second. So we're going to leave that as is. And then we have Planck's constant. So here we have 6.626 times 10 to the minus 34 joule seconds. The mass is 0.046 kilograms. And again, we need that to be in kilograms so that we end up with meters as our final unit. And the velocity is 30 meters per second. And since that's in meters per second, that's precisely what we want for the units. So let's see what we get here. And you can see that this wavelength is really, really, really short. Okay, so the second part of this is, at what speed must the ball travel to have a wavelength of 5.6 times 10 to the minus 3 nanometers? So we're going to use the same equation here. Only for this second part here, what we're going to do is we're going to rearrange this equation so that we have speed on one side and everything else on the other. So this is going to become the speed, the velocity is going to be h over m lambda. Now, the same thing here. If we want an answer of meters per second squared, the mass must be in kilograms, and the wavelength, we want it to be in meters, not nanometers. So this one's a little easier because we already have everything converted, or it's easy to convert. So we have 6.626 times 10 to the minus 34 joule seconds. That's Planck's constant, h. M is 0.046 kilograms. And for lambda, we're going to use 5.6 times 10 to the negative 3 times 10 to the minus 9 meters. So I want that wavelength to be in meters, so I take that n and I write 10 to the minus 9 instead, because that's exactly what n means. Okay, so here I'm going to take these two and cross them out. I'm going to write 10 to the minus 12. Because 10 to the minus 3 times 10 to the minus 9 is 10 to the minus 12. So let's take these three numbers and figure out what the velocity is. And that's going to be in meters per second. 6.626 second EE negative 34 divided by 0.046 divided by 5.6 second EE negative 12. And I get that the velocity must be, with two significant figures, 2.6 times 10 to the minus 21 meters per second squared. Okay, so there we go. That's how you use the de Broglie wave equation. All right, thank you much for listening. See you next time.